Hello again. In this video, we want to take a look at some difficult limit proofs. So these are the more difficult ones with epsilon and delta, where it's not a simple matter of factoring and canceling out a factor and then getting exactly the absolute value of x minus a. And ones like this, we sometimes have to choose an arbitrary value, which we typically pick 1, and we say delta won't be any bigger than 1. It'll be the minimum of 1 and some other value, which we'll find by assuming that it is smaller than 1. Now, we could have picked 2, or we could have picked 5, we could pick 10 billion, but let's face it, 10 billion is not close. And we're trying to get close to the values. That's the idea of the limit, getting close. So we want to take a look at this first limit that we have here. Here's an example of one where we're going to have to choose our delta to be the minimum of 1 and some other value. And again, the 1 is totally arbitrary. It's just relatively small. Another good choice would be 0.5. 0.5 is relatively small, but 1 is easier to work with as far as numbers go. So we start the same way. We split the proof into 2 parts. We've got the formal proof on the left side, which reads like a paragraph, more or less, with punctuation marks, capitalization at the beginning of sentences. On the right, we have the rough part, the Scratchwork side, which is really where all the real work takes place in order to find that thing that delta has to be smaller than. So we start with the absolute value of f of x minus L less than epsilon. So we're looking over here on this side, and we're going to start with our function less than L. So our function in this case is x squared, and our L is 16. Remember that a is the value that x is approaching, so it's 4. So what we're trying to get down at the bottom is the absolute value of x minus 4 less than something, all right? And we're trying to find this something in terms of epsilon and a number. So we just want epsilon in it. We don't want the variable x in it. And that's a problem here, because when we isolate it, we get x squared minus 16. We can factor x squared minus 16 into x minus 4 and x plus 4. And that gives us this line right here. Now, the next thing we want to do is we want to cancel the x plus 4s. And by dividing it on both sides to move it away, because it is not a part of what we're trying to find. Again, we're trying to get x minus a, which is going to be x minus 4, which is right here. So by dividing by x plus 4 in absolute values, we move that to the other side. Now, the issue is this expression doesn't just involve epsilon and the number. It also has the variable x in it. That's a no-no. We can't have x in there. This is why we choose delta to be smaller than some arbitrary number. We typically use 1 because 1 is easy to work with. So now I'm going to scroll down a little bit and let's see what we're doing. We're saying that delta is going to be the minimum of 1 and some unknown value. We don't know what this value is going to be. We're trying to find it. But if delta is less than or equal to 1, then remember we're approaching 4. So since we're approaching 4, then that means over here that I can write that x has to be between 3 and 5, all right? So it's got to be between 3 and 5 if my delta is less than or equal to 1. Because remember, delta is how far away from the a value you're going to be on the x-axis. Epsilon is how far you are away from the y value. Delta is how far away you are from the x value, which is a. So now that we have that x is between 3 and 5, we want to try to build this expression that we've got up here that we've got to get rid of. So the one we've got to get rid of is that 1 over absolute value of x plus 4. So we need to build a 1 over absolute value of x plus 4. Well, I could just go ahead and start and say, well, I can add 4 to all 3 parts. So if I add 4 to all 3 parts, then I can end up by saying that 7 is less than equal to x plus 4, which is less than equal to 9. And I can add the absolute values without changing anything because they're all strictly positive. So that's also true. Now, what I want to focus on is I want this to be larger than something else. So I'm going to focus on the right-hand side of the inequality. And what I want to do is I want to take this right-hand side of the inequality that we have right here, and I want to have it, I'm going to take the reciprocal of each one, which is actually going to reverse the sense of the inequality. In other words, I'm going to divide both of these parts by the absolute value of x plus 4 and divide both parts by 9. They're both strictly positive, so I don't worry about turning the symbol around. It gets turned around automatically. So I'm going to divide both sides by the absolute value of x plus 4. And I'm going to ignore the 7, which of course I could also divide it by the x plus 4 to keep it all the same. But I'm really only focused on the upper end right now because I want it to be larger than something. So now I've got 1 less than equal to 9 over the absolute value of x plus 4. The 9 has to go because when I was up here, I had epsilon over the absolute value of x plus 4. There was no 9. So the 9's got to go. So I'm going to move the 9 by dividing both sides by 9. And when I divide both sides by 9, I get 1/9 is less than equal to 1 over the absolute value of x plus 4. That means that I can take this expression and I can put it in up here and say that this means that epsilon over the absolute value of x plus 4 has to be greater than equal to epsilon over 9, and epsilon over 9 will be greater than the absolute value of x minus 4. But our delta, again, is going to be the minimum of 1 and this found value of epsilon over 9. So when we start the formal proof, we start the same way every time. We define what our function is, let f of x equal x squared, and let epsilon be greater than 0. So that's our typical steps that we follow right here. So we've got, if I can get my pointer to show up again. When we're looking at this part right here, we've got let f of x equal x squared, epsilon be greater than 0. Then the next thing we want to do is let delta be the minimum of 1 and epsilon over 9. So that's our next step. Let delta be the minimum of 1 and epsilon over 9. And then after we have that, then we can apply the rules in reverse that we found on this right-hand scratch side and apply them on the left. Once we say that delta is the minimum of 1 and epsilon over 9, then it's actually smaller than both 1 and epsilon over 9. And that means that I can replace delta with epsilon over 9. And so I have the absolute value of x minus 4 less than equal to epsilon over 9. And I start reversing the steps I did on the other side. Now, epsilon over 9 is less than equal to epsilon over the absolute value of x plus 4. I found that over here based on my assumption that delta was not going to be any bigger than 1. So then I replaced the epsilon over 9 with the expression epsilon over x plus 4. That means that that expression is greater than the absolute value of x minus 4. Then I multiply both sides by the absolute value of x plus 4. And of course, this leads to the product of two binomials. I multiply them together, then I can get my x squared minus 16. Then I restate the limit. I've proved the limit that as long as x minus 4 is less than this delta, then my function's distance from L, which is 16, will be less than epsilon. And I finish the proof by writing QED. Let's now move on to a different one that is pretty much the same, but a different function. Okay, let's now take a look at this next example. We're going to be working this one together. It's pretty much the same function. That's x squared. but this time the limit is 1 and we're approaching the value of a equal to 1. So we're going to work this one the same way that we did last time, and then we're going to come back and we're going to work it a slightly different way. Okay, so when we're looking at this, remember to start with the definition of the function minus L. Our goal, of course, is to get x minus a. So remember to identify the different pieces that you have. A is equal to 1 because we've got this value of 1 right here. So this is equal to 1. Our function value, which is going to be f of x, is equal to x squared. That's what you find inside the limit after the expression of the limit. The limiting value itself is what the limit is equal to, and that's going to be L. In this case, L is also 1, but this is L right here, and this is A. All right? Make sure you know which one is which. You don't want to get them mistaken one for the other just because they're both 1s. So we're going to start with f of x minus L, and we're going to try to end up with x minus A inside absolute values. We're going to have to play the minimum trick again, and hopefully we have enough room here to write it all in. So we're starting with f of x, which is x squared, minus L, which is 1, less than epsilon. Our next step will be to factor the left-hand side, which gives us x plus 1 and x minus 1 in parentheses, and then inside the absolute values less than epsilon. We want the x minus 1 because that is x minus a. The a value was 1. So we're going to divide both sides by the absolute value of x plus 1. That leads us to x minus 1 less than epsilon over absolute value of x plus 1. We like what we see. The only problem is we've got this variable x here in the denominator, and that can't stay there. So we're going to allow delta to be the minimum of some value that we pick at random, 1, and some other value which will depend on epsilon and a number, only a number. We can't have the variable in there. So we're going to choose delta to equal the minimum of 1 and something. And now we have to find that something. If we have a 1, then we know that we can then write that x, since it's approaching the value of 1, if it can't be further away than 1, then it's got to be between 0 and 2. If you're on the number line and you're at 1 and you want to go only one step to the left, that would take you to 0. One step to the right would take you to 2. So we know that x is trapped between 0 and 2, which means that x plus 1 is trapped between 1 and 3. Now we're going to focus on just the upper part of this inequality, the x plus 1 less than equal to 3. This is because we're going to divide by both of those factors, and then we will have the direction that we need. When we divide by both factors and put them in absolute values, since they're both strictly positive, this is going to give us 1 over 3 less than equal to 1 over the absolute value of x plus 1 in absolute values. Notice that the sense of the inequality has been reversed because x is on the opposite side of the inequality, but we did it without having to reverse the symbol because I did not divide by a negative, I divided by a positive. Now that I know that this 1 over x plus 1 is greater than or equal to 1/3, then I can replace that up here, and I can say that epsilon over x plus 1 in absolute values has to be less than equal or greater than or equal to epsilon over 3. So epsilon over 3 is less than equal to epsilon over absolute value of x plus 1. Remember that epsilon is determined to be a positive value. It's a distance from L on the y-axis. So it's strictly positive. So we're allowed to multiply both sides of the inequality by epsilon without changing the sense of the inequality. Now, the next thing that we want to do is we want to choose this to be our delta value. So we have absolute value of x minus 1 less than delta, which is going to be the minimum of 1 and epsilon over 3. All right. So we're going to choose it to be the minimum of one of those values. Now we'll start the proof, which basically reads, and this is the template that I've developed for my students that they use, which is let f of x equal something. Well, what does f of x equal? F of x is x squared, and let epsilon be greater than 0. Choose delta also to be a positive distance equal to the minimum of 1 and epsilon over 3. Then what can we write after that? Since it's the minimum of 1 and epsilon over 3, then if 0 is less than x minus 1, this basically means you can't get to 1. X can never get to a. Again, the limit is not what happens at the number, it's what looks like it's going to happen at the number. You never actually get there, which is what protects us from division by 0. All right, is less than delta, then we can write that the absolute value of x minus 1 is less than delta, which has to be less than or equal to epsilon over 3, which is less than or equal to, of course, our epsilon over absolute value of x plus 1. All right. Now that we have this inequality, note that we've got less than strict here, and we've got less than equal to, which actually delta is either less than epsilon over 3 or equal to it. Because epsilon over 3 could be larger than 1, and if it's larger than 1, then we'll choose 1 to be the smaller value. So it's possible that delta is smaller. It's either equal to it or smaller than it. And then we know that this is smaller than or equal to that, which means because we have the strict inequality here, that the absolute value of x minus 1 is strictly less than what's on the far right. And that will be the next thing that we write down. So we have the absolute value of x minus 1 strictly less than epsilon over absolute value of x plus 1. This is the difficult step and the difficult technique of proving this kind of limit. It's a sort of a trick, but trick is really just another word of saying a technique, a new technique, something a little more complicated than what we've done before. And considering that these are probably the hardest problems in all of Calculus 1, that's saying something. All right, so now we're going to multiply both sides by the absolute value of x plus 1, and that leads us to x plus 1. And then we've got multiplied by x minus 1 less than epsilon, which gives us the absolute value multiplied together of x squared minus 1 less than epsilon. Remember that what we're hoping to end up with down here is the function value minus L, and that's what we've got. Our function value was x squared, our L value was also 1, and so we've got the function minus L, and that's what this blank down here is telling you. You can stop when you get the function value minus L. So we have the function value minus L, so we don't need this line. We're going to rewrite the limit, and we write therefore, which one symbol is to write a colon followed by a period. Those 3 dots represent the word therefore, or thus, or hence, our 3 favorite therefore words. Therefore, the limit as x approaches 1 of x squared is equal to 1. In other words, I've said if you are within delta of 1 for the x on the x-axis, then the function will be within epsilon of 1 on the y-axis. And that was what we were trying to prove. So we're done, and we finish our proof with QED. Now, is there another way to work this same problem? Yes, there is. It's, to my mind, a more complicated method, but I'll show it to you so that you can see it. but there is another way to work this problem and get the same result. Let's rework the same problem, but use a different technique to prove that the limit exists. The format is basically the same. We're still going to start, we're still going to identify that this value here, a is equal to 1. This is our function, which is x squared. And L is what the limit is equal to. So that's our L value there. Then we're going to start on the Scratchwork side. We always start with f of x minus L. So we're going to again start with the absolute value of x squared minus 1 less than epsilon. This time, however, we're going to use the definition of the absolute value to rewrite this in a different way. This is just a different technique of solving the same type of problem. You can choose which one makes the most sense to you and then use that one to do your proofs. We're going to take the x squared minus 1. Since an absolute value it's less than epsilon, that means that on the number line, it's actually trapped between negative epsilon and positive epsilon. So I can write negative epsilon is less than x squared minus 1, which is less than epsilon. Now I want to isolate the variable x in the center of this triple part inequality. And so I'm going to solve for the x squared by adding 1 to each part. So when I add 1 to each part, I end up with, 1 didn't quite make, 1 minus epsilon less than x squared less than epsilon plus 1. Now I want to take the square root of each part. And notice here that when I do this, I am actually making the assumption that epsilon is smaller than 1. Do you see how that assumption in the previous method is sort of hidden in here? Because otherwise, when I take the square root of 1 minus epsilon, if epsilon is larger than 1, I've got a problem, all right? Because I'm taking the square root of a negative. So we're going to assume that epsilon is less than 1. So that's actually a part of this proof. So now we have 1 minus epsilon less than x less than the square root of epsilon plus 1. So actually we are making the same assumption, but we're just not making it explicit by writing it down. But we had to assume that epsilon was less than 1 to assume that this was a positive value so that we could take the derivative of it. So we're really assuming here that epsilon is less than or equal to 1, all right? So that the square root is not a negative underneath. Now, once we have this, we want to try to build what we need for the absolute value, which is the absolute value of x minus a. Our a value is also a 1, so we're going to subtract 1 from each part outside of the radical, and we get the radical of 1 minus epsilon minus 1 less than x minus 1 less than the radical of epsilon plus 1 minus 1. Now this next step is the tricky step, all right? The tricky step in that you have to think about the relative sizes of what you have now. When we look at this 1 minus epsilon, in order to take the square root, we had to assume that epsilon was smaller than 1. And that means that since epsilon is strictly positive, this 1 minus epsilon is now a number less than 1. So the square root of it is a number less than 1. And when I subtract this number less than 1 from negative 1, it's going to be negative. That's a problem because I need to trap this between two positive values, one with its opposite. So I'm going to actually factor out the negative and write it as negative times 1 minus the square root of 1 minus epsilon. Now I know that 1 minus the square root of 1 minus epsilon has to be a positive value. So this negative on the outside is the opposite of a positive value. And then I've got this less than x minus 1 less than, and the right side doesn't change. Now the technique on this side, and I'm running out of space, so I'll come to the bottom here. The technique on this side is to choose delta to be the smaller of these two distances here. Whichever one is smaller, that's the one I want to choose. This is a positive value inside the parentheses, and this is necessarily a positive value because epsilon's positive. So when I add 1 to it, it gets bigger than 1. And so it's something bigger than 1 minus 1 is still positive. So they're both positive values, and I want to choose delta to be the minimum of each one of those. So I'm going to choose delta to be the minimum of 1 minus the square root of 1 minus epsilon and the square root of epsilon plus 1 minus 1. I'll choose it to be the smaller of whichever those is. And then I can write that x minus 1 has to be between delta and negative delta. Since delta is the minimum of each of these, it's actually fitting inside of that inequality. And delta is going to be a strictly positive value because I guaranteed that both of these were positive values. So I have this between delta and negative delta, which means that I can then say that the absolute value of x minus 1, and I shouldn't have absolute values here yet, then I can say that the absolute value of x minus 1 is less than delta, right? By the definition of absolute value. So I don't have them here and I do have them here. So this is a more difficult, to my mind, proof to understand. It's a little bit trickier, it's more involved, but it does also work to do it, and it's working with the equation as written. Now we come up to the top and we start our formal side of the proof. Let f of x equal x squared and let epsilon be greater than 0. Choose 0 less than delta. We don't want to actually get to a to be the minimum of those two values, which were 1 minus, I got to find them again. 1 minus the square root of 1 minus epsilon and the square root of epsilon plus 1 minus 1. Whichever one of those is the smaller, then that's the one I want to choose. Such that, provided x doesn't ever get to a greater than 0, that's what the greater than 0 guarantees, then x minus a, which is the 1, will be less than delta. Now I've got to start at the bottom of my Scratchwork side and repeat all this work going backwards, which is a little bit of a trick. So we start with the absolute value of x minus 1 less than delta. Then we take off the absolute values by putting it between negative delta and delta. And then we put in the absolute values of the two that we had before that, which was the negative times 1 minus the square root of 1 minus epsilon, which might fit outside of that negative delta to delta range or might be equal to it, less than x minus 1, less than the square root of epsilon plus 1 minus 1, all right? Now remember that these are either equal to delta or they fit outside the delta range. So if they fit outside, then they definitely still work in the inequality. And once we get to this point, then we can rearrange and distribute the negative on the left and rewrite the terms as the square root of 1 minus epsilon minus 1 less than x minus 1 less than the square root of epsilon plus 1 minus 1. So we're repeating the steps going backwards up what we did on the right-hand Scratchwork side. The next thing we want to do is we want to add 1 to all 3 parts to get rid of the ones that we see here, here, and here. So we can isolate the x. So we add 1 to all 3 parts, which leads us to write the square root of 1 minus epsilon less than x less than the square root of epsilon plus 1. The next step, of course, is to square all 3 parts. Note that these are guaranteed to be positive because epsilon is a number greater than 0, and we made the assumption it was less than 1. So we're going to square all three parts, and we get 1 minus epsilon less than x squared less than epsilon plus 1. The next step, of course, is to move the 1 back into the center by subtracting it from each part. And this gives us negative epsilon less than x squared minus 1 less than epsilon. That's the definition of the absolute value there. So now we can write the absolute value of x squared minus 1 less than epsilon. That's what we're trying to prove. We started with x minus a less than delta and showed by algebra that this led to the absolute value of f of x minus L less than epsilon. Now that we have that part written down, we go ahead and rewrite the limit. Therefore, the limit as x approaches 1 of x squared equals 1. And we finish the proof with quo erat demonstratum, which again is quite enough, damn it. That was what we said in grad school, because by the time you got to the end of the proof, you were really, your brain was hurting. All right. Okay, let's go ahead and move on to another one and see another tricky epsilon delta proof. Okay, let's go ahead now and let's work our last tricky proof. This one is, the technique is more based on logic than it is on algebra. And that can make it more difficult because you have to sort of logic your way through the steps. So on this particular one, we're looking at the limit as x approaches 9 of the square root of x equal to 3. So we're going to identify again our a value. A is equal to 9. We'll identify our function value. F of x is equal to the square root of x. And we'll identify our limiting value, L, which is equal to 3. Now we're going to start on the Scratchwork side, and we're going to try to start with f of x minus L and try to end up with the absolute value of x minus a, which in this case is 9. So we want to end up with the absolute value of x minus 9. So what we're looking at here is we're starting with absolute value of f of x minus L. So that's going to be the absolute value of the square root of x minus L, which is 3, less than epsilon. Now, the next thing that we need to do is we need to somehow get this to be the absolute value of x minus 9. This is what we're aiming for down here at the bottom. We're aiming for this absolute value of x minus 9. And right now we've got this radical in the expression, which is not going to work. Now, how do we typically get rid of radicals? Well, typically we multiply by the conjugate of the radical expression. So we're going to do that here. We're going to take this square root of x minus 3 and place it over 1 to turn it into a fraction. We have to multiply by a form of 1 because the only things we're allowed to do to an expression on one side only is either to multiply by 1 or add 0. When you're not doing it to both sides, you're only allowed to do those two things, multiply by 1 or divide by 1, and add 0 or subtract 0. All right, but adding 0 means adding a number and subtracting the number, and multiplying by 1 usually means multiplying by some expression divided by itself. In this case, the conjugate of the original radical. Now we've got this expression. Our numerator then becomes what we wanted. Remember that the difference of two squares pattern, you get the first one squared, which gives you x. The outside gives you a positive 3 radical x. The inside gives you a negative 3 radical x. They cancel and go away. And negative 3 times 3 gives you minus 9. This is that difference of two squares pattern, also called a conjugate pair. However, we still have the radical of x plus 3 in the denominator. And this is a problem. it's a problem because if I divide by it, I'm going to put it over here and it's going to be multiplying epsilon by it. And I don't want that. So I've got to think about this in a different way. If I were dividing by it, it would be easier. I could set it to be the minimum of some value and some other one. But since this is being divided by it already, I'd have to multiply by it. So I need to think about this in another way. And I'm going to think about this as being a fraction less than epsilon. And I want to trap this x minus 9 less than epsilon. So when I think about this as a fraction, I need to think about what would make that fraction be the largest possible value. And remember, x is getting close to 9, which is our a value. So we don't have to worry about a negative under the radical. That's not going to happen. X is getting close to 9. So the values are going to be like 8.9, 8.99, or 9.01, 9.001. We're getting close to 9. All right, close. So we're not at -5. We don't have to worry about negatives under the radical. When we look at the fraction, though, remember what happens with fractions. To make the fraction be as large as possible, you need the denominator to be as small as possible. The whole fraction becomes as big as possible when the denominator is as small as possible. And I want this fraction to be less than epsilon. So if I think about the absolute largest value it could possibly take on, what is that largest possible value it could possibly take on? Well, that would be when x is 0, right? Which isn't close to 9 at all. But that would make this denominator as small as possible. This is the square root of x. And the smallest it can possibly get is 0. The smallest denominator is then 3. So if the smallest denominator is going to be 3, then I know that I can write this expression right here of absolute value of x minus 9 over the square root of x minus, or plus 3 rather, has to be less than or equal to the absolute value of x minus 9 divided by 3. And I want this to be less than epsilon, right? So since I know that I want it to be less than epsilon, do you see what's coming? Of course. Now that I've got a constant here and I don't have the variable x, I can multiply both sides by the 3, and that will isolate the absolute value of x minus 9. So this gives me absolute value of x minus 9 less than 3 epsilon. So this time it turns out that I don't want something smaller than epsilon. I actually can take 3 times epsilon and it would still work. All right. So could I take something smaller? Yes, of course. You can always go smaller, but you can't go bigger. All right. So now I start on the formal side with let f of x equal the square root of x and let epsilon be positive, greater than 0. Choose delta to be positive, greater than 0, and let delta be equal to 3 epsilon, such that if the distance x is from A is strictly positive, it never gets to 9, it just gets close to 9, then we can start with the absolute value of x minus 9 less than delta equal to 3 epsilon. Then we can divide both sides by 3. That gives us x minus 9 over 3 less than epsilon. Now we can write the next part, which was the part that we had right here. All right. So now we can write that the absolute value of x minus 9 over the square root of x plus 3 has to be less than or equal to the absolute value of x minus 9 over 3, which is less than epsilon. Now we've got a strict inequality here, which is between the epsilon and the expression that we want on the left. And so the next thing that we're going to do is we're going to drop the middle part and keep the strict inequality. And then we're going to, of course, factor the numerator. x minus 9 into the square root of x plus 3 and the square root of x minus 3. So then we get the square root of x plus 3 and the square root of x minus 3, all divided by the square root of x plus 3 in absolute values strictly less than epsilon. We can cancel those, and that gives us our f of x minus L less than epsilon, which is what we were trying to prove. We started with absolute value of x minus a less than delta, and we showed through algebra and logic that we could reach the absolute value of f of x minus L less than epsilon. Now we restate our limit down here at the bottom. Therefore, the colon followed by a period, the limit as x approaches 9 of the square root of x is equal to 3. And then we end the proof with QED. And don't forget to put a period after your limit. So these were all the more difficult limit proofs that I wanted to do for you. I hope this made some sense and that you could follow the logic of them. It will probably take you some time to actually get to the point where you feel like you might be able to write one of these yourself. It takes some time for the logic to really sink in. Just go over them and over them again and again, predicting at each step, what's the next step I should do? What's the next step I should do? And I think you'll find that they'll start to come more easily.